For decades, medical school professors taught a rigid rule about the human brain. The consensus held that you were born with all the nerve cells you would ever have, and from that point on, your biology was a slow slide into decline. When Robert, an oncologist, noticed a strange pattern in his clinic, it contradicted everything he had been taught. His patients were beating cancer and surviving their treatments, yet shortly after being cleared of the disease, many fell into a state of severe depression. Surviving a life-threatening illness should, in theory, bring relief. There was no clear psychological reason for such a heavy crash in mood to occur right at the moment of clinical victory. The timing suggested a link to the medical treatment itself. The drugs used to eliminate cancer appeared to be impacting the physical structure of the brain at the same time they were targeting the tumors. To find that link, we have to look at the way standard cancer treatments function. They are designed to stop cells from multiplying, effectively freezing rapid division to starve the tumor. This chemical freeze circulates through the entire body. When it reaches the brain, it halts any ongoing cellular multiplication, a side effect that correlates directly with the onset of clinical depression. This reveals that the old medical textbooks were missing a piece of the puzzle. The adult human brain creates new nerve cells every day. This process is known as neurogenesis. This discovery changes our model of neurology. The brain is a self-renewing organ, replacing its own components throughout an entire lifespan. This regeneration is localized in a specific gray structure in the center of the brain called the hippocampus. The scale of this growth is surprisingly consistent. Every day, the adult brain produces approximately 700 new nerve cells. That daily production rate was estimated by Dr. Jonas Friesen and his team at the Karolinska Institute. While 700 cells might seem minor compared to the billions we possess, the cumulative effect is massive. At age 50, every neuron in the hippocampus you were born with has been replaced by an adult-born neuron. Over a lifetime, the brain's emotional and memory center is physically rebuilt. The structure we rely on to process the world is essentially a different organ than the one we had as children. These new cells perform specific, critical tasks. They determine the quality of our memory, specifically helping us navigate spatial environments and distinguish between similar events. They allow you to remember the slight difference in where you parked your bike this morning compared to yesterday. They prevent your daily routines from blurring into a single, indistinguishable memory. These neurons also regulate mood. Research shows a direct link between the volume of new cell production and the brain's ability to ward off depressive symptoms. Without this daily supply of cells, memory quality fades and mood stability falters. This explained why Robert's patients became depressed. Their treatment had temporarily paused the brain's ability to maintain itself. Since our memory and mood depend on these 700 daily cells, the next question is one of control. Can our behaviors change the rate at which we produce them? Early evidence from the Salk Institute proved that neurogenesis is highly responsive to environment and activity. In laboratory studies, a mouse with access to a running wheel showed a dense cluster of new neuron growth, while a mouse in a standard cage showed only a sparse scattering of new cells. Specific choices act as a brake on this growth. Chronic stress levels, a lack of sleep, and high saturated fats all work to decrease the daily production rate. Conversely, other habits act as accelerators. Active daily learning, aerobic exercise routines, and intermittent fasting have all been shown to increase the number of new neurons the brain generates. Even specific nutrients make a difference. Flavonoids found in blueberries and dark chocolate, along with the omega-3 fatty acids in fatty fish, provide a measurable boost to cell production. Research even suggests the texture of our food matters. Crunchy foods that require active chewing appear to promote neurogenesis, whereas a soft diet can actually impair it. Every meal, workout, and sleep cycle provides a biological instruction to the brain. We are constantly signaling the hippocampus to either continue building or to begin to stagnate. For Robert's oncology patients, the pause in neurogenesis was a medical side effect. The drugs required to save their lives briefly interrupted their brain's natural growth cycle. For most people, however, the production of these cells is a process that responds to individual behavior. Outside of a clinical setting, we can influence this rate of growth through our daily habits. This marks a shift in how we view cognitive health. The human brain is an active construction site, capable of ongoing repair and expansion. By choosing the activities and foods that trigger new growth, we take on the role of the architect, determining the longevity and quality of our own minds.